Dear students, welcome to our course Mathematical Methods. Today we are going to discuss the third module in our fourth unit entitled Lorentz series. The learning objectives in this module are to study the Lorentz series expansion of a given analytic function on an annular region and to practice the related problems. So, Lorentz power series representation of a given function and an annular region. So, before to study the Lorentz power series representation, we have to recall the concepts which we have studied in the earlier modules. We studied that if a function f of z is analytic at a point z0, then it can be expanded in Taylor series about the point z0. But if f of z fails to be analytic at a point z0, then we cannot apply Taylor's theorem at the point z0. Then, in these situations, there is a possibility that however, to find a series representation for f of z by involving both positive and negative powers of z minus z0. Such type of power series representation is called Lorentz series. We now represent the theory of such power series representation. Let us see the statement, my dear students. Suppose that a function f of z is analytic throughout an annular domain, which is R1 less than mod of z minus z0 is less than R2, centered at z0, and let C denote any positively oriented simple closed contour about the point z0 and lying in the domain. Then, at each point in the domain, f of z has the power series representation as follows. That is, f of z is equal to summation of an times z minus z0 whole to the power of n, where summation runs from 0 to infinity, plus summation of bn times z minus z0 whole to the power of minus n, where summation runs from 0 to infinity. Students, observe here, we are expressing the power series representation in both positive and negative powers of z minus z0, which was defined over R1 is less than mod of z minus z0 is less than R2. Let it be equation 1, where the coefficients an and bn are given by an is equal to 1 by 2 pi I times integral over c f of z by z minus z0 whole to the power of n plus 1 into dz, where n runs from 0, 1, 2 and so on. Let it be equation 2. And bn is defined as 1 by 2 pi I times integral over c f of z by z minus z0 whole to the power of minus n plus 1 times of dz, where n is equal to 1, 2, 3 and so on. Let it be equation 3. Now, by clubbing these two summations as one term, we can write the another form of the Lorentz series. That is, the another form of the Lorentz series is given by f of z is equal to summation cn times z minus z0 whole to the power of n, where the summation runs from minus infinity to plus infinity, defined over the annular region R1 is less than mod of z minus z0 is less than R2, where the coefficient Cn was defined as Cn is equal to 1 by 2 pi I times integral over c f of z by z minus z naught whole to the power of n plus 1 times dz, where n is any integer. That is, n is equal to 0 plus r minus 1 plus r minus 2 and so on. So, by studying the Lorentz power series representation of the function f of z on an annular region, we can learn some notes on this Lorentz series expansion. So, first recall what is Bn. We have studied in equation 3. Bn is equal to 1 by 2 pi I times integral over c f of z by z minus z naught whole to the power of minus n plus 1 dz, where n is equal to 1, 2, 3 and so on. Students, observe the integrand of this Bn, that is f of z by z minus z naught whole to the power of minus n plus 1. If I take the denominator to the numerator, then I have the integrand will be f of z times z minus z naught whole to the power of n minus 1. That is, the integrand in equation 3 can be written as f of z times z minus z naught whole to the power of n minus 1. Thus, it is clear that when f of z is actually analytic throughout the disk, mod of z minus z naught is less than r2, the integrand f of z times z minus z naught whole to the power of n minus 1 is also analytic on the disk, mod of z minus z naught is less than r2. Hence, all the coefficients are Bn or 0. How? Can you remember that? A result called Cauchy integral theorem. What it says? If f of z be analytic and f dash of z be continuous in a simply connected domain, then integral over c f of z dz is always equal to 0 along every simple, smooth or piecewise smooth closed curve C contained in the simply connected domain capital D. In that way, all the Bn's are all equal to 0. And by the Cauchy integral formula for derivatives, we have, can you recall the Cauchy integral formula for derivatives, my dear students? Can you recall? Yes. Let f of z be analytic in a simply connected domain capital D. If z0 be any point in capital D and C is a simple closed curve in the domain capital D enclosing the point z is equal to z0, then f of z has derivatives of all orders in the domain which are also analytic in the domain capital D, and further we have 1 by 2 pi I times integral over c f of z by z minus z naught whole to the power of n plus 1 dz can be written as nth derivative of f at z naught divided by n factorial, where n runs from 1, 2, 3 and so on, where the curve C is traversed in the anti-clockwise direction. So, from this result, an can be written as? Yes. An is equal to 1 by 2 pi times of 1 by 2 pi I times of integral over c f of z by z minus z naught whole to the power of n plus 1 dz can be written as nth derivative of f at z naught by n factorial. So, thus the expansion 1, that is the Lorentz series expansion, can be reduced to f of z is equal to summation of an times z minus z naught whole to the power of n. Mod of z minus z naught is less than r2, where an is nth derivative of f at z naught by n factorial, which represents Taylor series representation about the point z is equal to z0. That means we have deducted the Taylor series from the Lorentz series expansion. Now, the second point on this Lorentz series is, if f fails to be analytic at z0 but is otherwise analytic in the disk, mod of z minus z naught is less than r2, then the radius r1 is chosen arbitrarily very small, and the condition of validity of the Lorentz series is the punctured disk 0 less than mod of z minus z naught is less than r2. Similarly, if f is analytic at each point in the finite complex plane exterior to the circle of convergence C, that is mod of z minus z naught is equal to r1, then the condition of validity of the Lorentz series is r1 is less than mod of z minus z naught is less than infinity. And note that if f is analytic everywhere in the entire finite complex plane except at the point z0, then the condition of validity of the Lorentz series is valid at each point of the analyticity, or when 0 is less than mod of z minus z0 is less than infinity. As we studied that the Taylor series can be computed through the binomial series expansions. So in the same way, the Lorentz series also can be computed through some binomial expansions, where in actual method we have very, very tedious calculations to find the Lorentz series expansions. So it is difficult to obtain the Lorentz series expansions using the equation 1. So since the Lorentz series has a uniqueness property, it can be obtained by various other methods like binomial expansions, etc. Please remember, my dear students, we can express the Lorentz series by using binomial series expansions. So by gathering all the information, we can study now the examples. Let us take example 1. Find all possible Taylor's and Lorentz series expansions of the function f of z is equal to 1 by 1 minus z about the point z is equal to 0. Let us see the solution. Notice that f of z is 1 by 1 minus z is analytic for all z except at z is equal to 1. Therefore, we consider the regions with the center at z0 is equal to 0, or can you guess? Yes. First one is mod z is less than 1, and another one is mod z is greater than 1. Now see, on the region mod z is less than 1. Inside this region, the function f of z is analytic, and hence we can obtain the Taylor's expansion about the point z0 is equal to 0. Thus, the Taylor series of f of z is equal to 1 by 1 minus z about the point z0 is equal to 0 is given by 1 by 1 minus z can be written as 1 minus z whole to the power of minus 1. We have the binomial series expansion, that is summation of z power n, where mod z is less than 1. Now on mod z is greater than 1. For this region, we have the Lorentz series with 1 mod of 1 by z is less than 1. Why I am writing like this? Can you guess, anybody? Yes, because to apply the binomial series expansions, I need this condition mod of 1 by z is less than 1. So you have to remember this, guys. To apply the binomial expansions, we need such type of conditions. In further problems also we can do all these things. Since we have mod z is greater than 1, we can write that mod of 1 by z is less than 1. Thus, the Lorentz series of f of z is equal to 1 by 1 minus z about the point z0 is equal to 0 is given by 1 by 1 minus z can be written as, I am taking minus z as common, we have 1 minus 1 by z, and which is equal to minus of 1 by z times, I am taking this term to the numerator, I will get 1 minus 1 by z whole to the power of minus 1. Based on this condition, I can apply the binomial series expansions. That is minus 1 by z times 1 plus 1 by z plus 1 by z square plus and so on. That is f of z is equal to 1 by 1 minus z. By multiplying with minus 1 by z, we can get minus times 1 by z plus 1 by z square plus 1 by z cube plus and so on. So, which is equal to minus of summation 1 by z power n, where n runs from 1 to infinity. The validity of this series is mod z is greater than 1. Now take the second example, my dear students. Find all possible Taylor's and Lorentz series expansions of the function f of z is equal to 1 by z plus 1 times z plus 2 whole square about the point z is equal to 1. Let us take the solution. Notice that the function f of z is analytic for all z except at z is equal to minus 1 and z is equal to minus 2. So the distances between the point z is equal to 1 and the points where the function is not analytic, that is z is equal to minus 1 and z is equal to minus 2, are 2 and 3 respectively. Therefore, we consider the regions with the center at z0 is equal to 1 as number 1, mod of z minus 1 is less than 2, and number 2, 2 is less than mod of z minus 1 is less than 3, and mod of z minus 1 is greater than 3. We now rewrite the given function f of z as 1 by z plus 1 times z plus 2 whole square. Can you split the function by using the partial derivatives, my dear students? How can you write this? A by z plus 1 plus b by z plus 2 plus c by z plus 2 whole square. In that pattern, you have to split into partial fractions, find a, b, c values, and you have, this is the partial fractions of this function f of z. Did you get this? Yes. Now I am rewriting this 3 terms as in terms of z minus 1. That is, first one can be written as 1 by z minus 1 plus 2 minus 1 by z minus 1 plus 3 minus of 1 by z minus 1 plus 3 whole square. On mod of z minus 1 is less than 2. In the first region, we have inside this region the function f of z is analytic, and hence we can obtain a Taylor series expansion about the point z0 is equal to 1. Therefore, the Taylor series of f of z about the point z0 is equal to 1 is given by f of z is equal to the first term 1 by z minus 1 plus 2 can be written as, taking 2s out, then we have 1 by 2 times of 1 plus z minus 1 by 2 whole to the power of minus 1. Similarly, the second term can be rewritten as 1 by 3, taking out, and we have the remaining 1 plus z minus 1 by 3 whole to the power of minus 1. In the same manner, we can write the third term 1 by 9 times 1 plus z minus 1 by 3 whole to the power of minus 2. Now we have the binomial expansion that 1 plus z whole to the power of minus 1 is summation of minus 1 whole to the power of n z power n under the condition of validity mod z is less than 1. Here we have mod of z minus 1 is less than 2. Therefore, we can expand the first term as 1 by 2 times of summation minus 1 whole to the power of n z minus 1 by 2 whole to the power of n. The second term minus 1 by 3 times of summation of minus 1 whole to the power of n times z minus 1 whole to the power of n by 3. And for the second one we have the power is minus 2. We have the expansion 1 plus z whole to the power of minus 2 can be written as summation of minus 1 whole to the power of n times n plus 1 into z to the power of n under the condition of validity mod z is less than 1. So we can write the third term minus 1 by 9 times summation of minus 1 whole to the power of n times n plus 1 into z minus 1 by 3 whole to the power of n. Therefore, by simplifying the things, you have this step. Dear students, please simplify this and verify yourself. And again simplifying, we have this step. Summation of minus 1 whole to the power of n times 2 power minus n minus 1 minus of n plus 4 times 3 power minus n minus 2 times z minus 1 whole to the power of n. Now we see the condition of validity of this power series expansion. Notice that the first series is valid in mod of z minus 1 is less than 2, and the second and third series are valid on mod of z minus 1 is less than 3. So by taking the common condition of validity, the sum is valid in mod of z minus 1 is less than 2. Now coming to the second region on 2 less than mod of z minus 1 is less than 3. For this region, we have the Lorentz series expansion within the region that mod of 2 by z minus 1 is less than 1 and mod of z minus 1 by 3 is less than 1. Because since we are writing these two conditions to get the binomial expansions. Thus, the Lorentz series of f of z about the point z naught is equal to 1 is given by f of z is equal to, in the first term we are taking z minus 1 as common and write this, and second one we are taking 3 as common in the denominator and simplifying that we have this, and in the third also we are taking 3 as common, simplifying that we have, and applying the binomial expansion that 1 plus z whole to the power of minus 1 for the first and second one. So we have this summation 1 by z minus 1 times summation of minus 1 whole to the power of n times 2 by z minus 1 whole to the power of n. Similarly for the second one. In the third term we have the power is minus 2. So recall the binomial expansion for 1 plus z whole to the power of minus 2 is this, and based on this formula we are writing that minus of 1 by 9 times summation of minus 1 whole to the power of n into n plus 1 whole times z minus 1 by 3 whole to the power of n. So simplifying the terms, we have this step, my dear guys. Please simplify and verify yourself. So now the condition of validity of this power Lorentz series expansion is, so notice that the first series is valid on mod of z minus 1 is greater than 2, and the second series is valid on mod of z minus 1 is less than 3. Therefore, the sum is valid in the annular region 2 is less than mod of z minus 1 is less than 3. Now coming to the third region, mod of z minus 1 is greater than 3. Since mod of z minus 1 is greater than 3, for this region we have the Lorentz series with mod of 3 by z minus 1 is less than 1. My dear students, please verify this condition based on the given region to get the binomial expansion for the function f of z. Since we have this mod of 3 by z minus 1 is less than 1, and hence we have the condition mod of 2 by z minus 1 is less than 1. Thus, the Lorentz series expansion of f of z about the point z naught is equal to 1 is So now first f of z can be rewrite. The first term can be rewrite as by taking z minus 1 as common in the denominator. We can write similarly the second one and third one. Recall the binomial expansion and apply for the first, second, we have this one. For the first one and second one, and in the third term we have power is minus 2. Recall the formula and you can write this one. Therefore f of z is equal to, by simplifying the above three terms, we have summation of minus 1 whole to the power of n times 2 power n minus 3 power n by z minus 1 whole to the power of n plus 1 minus 3 power n times n plus 1 by z minus 1 whole to the power of n plus 2. Please simplify, my dear students, then only you can get the concept and verify yourself. And the sum is valid in the region mod of z minus 1 is greater than. So we are coming to the end of our module. Please go through your material which we have provided to you. Learn the problems properly and study the definitions first before solving the problems. Then you will get the concept in a good way. Anyhow, thank you, my dear students. Thank you.